We want to show that if we take a vector x and we apply a rotation matrix A to it, that the length in R2 is going to be the same. So basically that rotation doesn't change length, it just sort of changes where it points to. So the length of x, we know, is, well, if we say that x is, let's call it xy. So the length of x is the root of x squared plus y squared. And so if we're going to figure out the length of ax, we're going to have to actually sort of write that out. So ax, since A is a rotation matrix, it's cos theta negative sine theta, and cos theta times my vector x, which would be xy. And so if I multiply this out, I'm going to get x cos theta minus y sine theta, and then x sine theta plus y cos theta. And so the length of this, it's the same formula, it's just I have these sort of messy expressions to throw in there. So the length ax is going to be the square root of sort of this big expression here, x cos theta minus y sine theta squared plus x sine theta plus y cos theta squared. A little bit more space. And so really all I've got to do with this is expand and simplify. And that's what I'm going to do and just hope it kind of works out. So I'll put the root on after, but I'll use my squaring formulas. So I'll square the first, 2 times the first times the second, and square the second, and I'll make it positive. So that's the first term. And then the second one I'm going to square. So again, square the first, 2 times the first times the second, and it's the plus this time. And square the second. Hopefully you kind of see what's happening here. And I'm gonna, there, I'll use a straighter line on that one. So hopefully you can see that these two middle terms are actually identical and they're going to cancel each other out. And what I'm going to do now is regroup for the x squared and the y squared. And you might see something familiar in there. So I'm going to get x squared, and I've got cos squared theta plus sine squared theta. And then on the y squared, you can see we've got sine squared theta plus cos squared theta in the second term. And if you don't recall, hopefully that does look at least a little bit familiar, but we get to use the Pythagorean identity here. If you recall, sine squared theta plus cos squared theta is equal to 1 for all theta. It doesn't matter what theta you choose. Anything you plug in, you're going to get 1. That's the Pythagorean identity. And it's very useful. Oh yeah, that basically actually just means that what we've got is x squared times 1 plus y squared times 1. And as you can see, that's the exact same thing that we had for the length of x. So they're the same.